Okay, it's 2:02 now. I think we can get started. So hello, everyone. Welcome to Ask Seminar series. I'm John, the seminar coordinator. And together with me is Miss Kathy Medney. Kathy and I will be today's moderator. And our associate director, Ralph Ferrero, also join us. Just so you know that this seminar is being recorded, and we will publish the video recording on our YouTube channel. So please feel free to check it out. It usually will take like a couple of days. And the Q&A session is right after the presentation, so please feel free to ask any questions. You can also chat us the questions. And today we are excited to have our distinguished speaker, Dr. Clara Desser, joining us from UNCA. And before she gets started, our Associate Director, Ralph Ferrero, will be introducing her. Ralph, please go ahead.
Yeah, thanks, John. And yeah, welcome, Clara. We look forward to your talk here in a few seconds. She's senior scientist and head of the climate analysis section at NCAR. Got her PhD from the University of Washington not too long ago. And, she's a world-renowned expert in climate modeling, has done a lot of work with impacts of sea ice changes, published quite a few papers on this topics. Also involved with a lot of community climate activities, with code sharing, and also involved with the U.S. CLIVAR project, amongst other things. And so I'm just going to turn it over to Clara, and we'll learn a bit about trying to predict some circulation changes here.
Well, thank you so much. And thanks everybody for joining. I really appreciate this opportunity to share some recent work with you, and very much look forward to a discussion after the seminar. And it kind of feels like yesterday that I got my PhD. I guess these things never really disappear. Anyway, so today I will talk about projected changes in unforced modes of atmospheric circulation variability over the North Pacific in a coupled model large ensemble. And this work is recently published. It's available on the early online release at Journal of Climate. And it was led by my postdoc, J.P. O'Brien. And again, this is, I would say, the tip of the iceberg of what one can learn about how atmospheric circulation variability may change in a warming climate. And I think there's a lot of rich potential for additional scope and expansion of these ideas. Okay, so we'll just get started. Start with a very broad brush overview here on the topic. So, of course, anthropogenic emissions, principally from greenhouse gases and sulfate aerosols from industrial activity, is, of course, altering our climate system, and this will intensify as long as we are continuing to emit CO2 into the atmosphere. So these anthropogenic influences are twofold. They can, of course, alter our mean climate, so sort of a slowly evolving climate state. And they can also alter the variability in the climate system that is internally generated. So we've really, as a community, focused on this mean state change. So how is the mean climate going to change as humans alter their environment? So this is very well studied. For example, the various IPCC reports encapsulate, I would say, the state of the art of what we know about the mean state changes. But I think now there's an emerging focus amongst researchers in our community on how anthropogenic influences may alter the variability in the climate system. This is a more challenging topic because you need a lot of samples of the variability to really distinguish whether there are forced changes in the variability or whether it's just sort of a sampling issue and it's not attributable to anthropogenic emissions. So that's going to be my focus here today. Just very, very briefly, of course, this general topic about forced changes in variability has been studied and is continuing to be studied. I would say the most attention has been paid to how precipitation variability may change with climate change. And I can point you to a recent paper, Pendergrass et al., that indicates how precipitation will become much more variable on a broad range of timescales, both drought and pluvials, extreme precipitation, the intensity of precipitation, et cetera. That really is going to change under climate change. There's also been some attention paid to how near surface air temperature variability may change in the future. And I would say we have a good physical understanding for the projected decrease in the variability of air temperature at high latitudes that is directly causally related to the loss of Arctic sea ice. ENSO, of course, is a very a primary focus, and I would say still a lot to be understood about future changes in ENSO. The types of coupled models that we have to date suggest that there will be an increase in both extreme El Nino events and La Nina events, but there is large model dependence to this result. And then finally, we come to the atmospheric circulation. There's been a lot less work done in this realm, and I think this is really where we have some low-hanging fruit to really probe. There is indication that as ENSO variability intensifies, so will the teleconnections that ENSO drives. And also an indication that the North Atlantic Oscillation, a primary mode of variability in the atmosphere over the North Atlantic sector, that may also intensify with climate change. So today I'd like to carve off a small piece of the pie here and look at a sort of more general view of how the large-scale atmospheric circulation over the North Pacific in the winter how its variability may change under anthropogenic emissions. So we'll address two different questions. The first, which is what I will pay most attention to, is how will anthropogenic emissions affect the leading modes of internal variability in the North Pacific atmospheric circulation and their associated impacts on precipitation. And then secondly, towards the end of the talk, we'll look at how large are these projected changes in variability compared to the changes in the mean state. Do we really need to care about the changes in variability, or are they second order? And for the approach we'll be using, I've become enamored of a fairly new analysis technique, or at least new to climate science, and that is so-called snapshot empirical orthogonal function analysis. And I'll walk you through what that is. And we will apply this analysis tool to the CESM1 coupled model large ensemble, which spans the years 1920 to 2100. And I'll also tell you in detail what that model set of model simulations is. Okay, so our study region, this is the focus here, the North Pacific Ocean and western part of North America. And we're decided to use this as our focus, at least for this initial study, because it's such an interesting area where you have both intrinsic mid-latitude variability. So the jet stream and the associated storm track have a lot of variability from day to day, year to year, decade to decade. And this region, of course, is also influenced by teleconnections from El Nino Southern Oscillation that takes place in the tropical Pacific. So it's an interesting kind of nexus region for both intrinsic mid-latitude influence or dynamics plus teleconnections from the tropics. So we will be looking at the 500 hectopascal geopotential height field, and we'll look at the boreal winter season, so 3-month averages, December, January, and February. And we'll be looking at departures from the climatological mean. So we're looking at just anomalies and the variability thereof. And as you'll see as we go along, when we conduct this snapshot EOF analysis, we're actually going to be looking at the first 3 modes of variability. Normally, I don't look much beyond mode number 1, but it turned out mode number 3 was particularly interesting for this application. So very loosely speaking, mode 1 can be resembles closely the so-called Pacific North American pattern or PNA pattern. Mode 2 corresponds to what's called the North Pacific Oscillation, with elements also of the West Pacific pattern. And then mode 3 is looks a lot like the East Pacific pattern. So if you're not familiar with these nomenclature, these are well-known teleconnection patterns that have been studied in observations from a number of different approaches. One can probe these patterns further and decompose them using rotated EOF analysis and other types of analysis tools. And I leave that to future work. And here we're just focusing on these 3 modes for the time being. Okay, and I should say that I won't show it to you, but we have carefully compared how the model that we're using, how it reproduces the observed modes of variability. And for these 3 modes, it does an excellent job depicting both the spatial patterns and amplitudes of these 3 teleconnection patterns. Okay, so moving on. So as I mentioned, we're going to be looking at some model simulations, and these are part of what is called the CESM1 Large Ensemble project. This was a big undertaking led by NCAR, but with enormous community participation. And I know a lot of people have since used these simulations for so many applications. So I think this is a perfect setup for looking at these questions of how industrial emissions can force changes both in the mean state of our climate system, but also in the variability of climate about that mean state. So this project is a set of simulations that's conducted with the Community Earth System Model version 1. There's now a version 2, but when we did this work, that model setup was not complete. So we've used version 1. This is a global model. The spatial resolution is approximately 1 degree in latitude and longitude, so fairly high resolution as these global models go. It's fully coupled. It has representations of the atmosphere, the ocean, sea ice, land, and some representation of biology. And there are a lot of papers documenting, the strengths and shortcomings of this model. But overall, I would say it is realistic enough that I think it's a very useful tool. So the way that these simulations were conducted, I'll just walk you through the experimental design here in case you're not familiar. So these coupled models, they are typically one has to, make sure that they're in some kind of quasi-equilibrium amongst the different components. In particular, the ocean, you want to make sure that things are spun up. So first, there's a long run with just the ocean to get that into some kind of balance. And then typically, or in this case in particular, we conduct a long pre-industrial control simulation. So that's where we keep the radiative forcing at conditions representative of the year 1850 as best they are known. And then we let the coupled model produce its own variability under that constant radiative forcing condition. And then in the year 401, when we deemed this coupled simulation to be in quasi-equilibrium, we then began the historical and future radiative forcing simulation, and that goes all the way to the year 2100. And this uses historical radiative forcing up to the year 2004, I believe, or 5. And then thereafter, it uses the RCP 8.5 emissions scenario. So I call that the hammer. That's what we're going to be, subjecting these simulations to, this typical CMIP style exercise of forcing. What's new here in the large ensemble is that we run a whole bunch of these simulations with the same model and the same radiative forcing, except that on the 1st of January 1920, we've introduced a tiny perturbation to the atmospheric temperatures on the order of the model's round-off error. So this is 10 to the minus 14 degrees Kelvin, really not anything we would measure. And then we run another 39 simulations, each of which has this small, random, tiny initial condition perturbation just to the atmospheric temperatures. So then we run these, and you can think of this tiny perturbation as the butterfly effect. This is really the chaos theory or paradigm that Ed Lorenz introduced to climate science in the early 1960s. And to the extent that each of these simulations starts to sort of take a different trajectory, this is this ensemble spread, if you will, across the 40 simulations. That can only be due to internal variability in the model's climate, the way that these simulations are designed. And therefore, this is irreducible spread. And it's largely unpredictable. There's a little bit of memory of the initial ocean condition in 1920, but that pretty much disappears after about 10 years. And then from 1930 onward, you can think of each of these simulations as taking kind of its own path, if you will. It's generating its own sequence of internal variability that's superimposed upon a common radiatively forced response. So let me just put this take it from words and actually give you a concrete example of these simulations. So here I've picked out just a time series of the Nino 3.4 SSTs a well-known index for ENSO. And this is just the time series of these boreal winter Nino 3.4 index from the first simulation of the CESM1 Large Ensemble. So this runs from 1920 to 2100, and the positive value, the high values here would be indicative of the model's El Nino events, and the low values would be indicative of the model's La Nina events. So that's the first simulation. Then we can look at the second ensemble member. And as I alluded to before, each member can have El Nino and La Nina events, or internal variability in general, take a different sequence. So in ensemble member number 2, the El Nino events happen to occur, can occur in different sets of years from those in ensemble member 1, and likewise for La Nina events. And then just to make this point hit home, this is the third ensemble member. So again, the variability or the occurrence of El Nino and La Nina events can happen in different years in these different ensemble members. But you can see that they all have this common background climate change signal embedded in them, and that's because of the radiative forcing that is being imposed to each ensemble member. So if we want to isolate the variability from the background climate change, we can do that in a very simple way with these large ensembles. We can simply take the average of all 40 simulations at each time step and subtract that average, or the ensemble mean, from each ensemble member to get the deviations from the ensemble mean. And when we do that, we get rid of background climate change, and now we're just looking at pure variability. So this is internal variability by design, because we've taken out the forced response by subtracting the ensemble mean. But the important thing here is that the variability can also change with climate change. So there can be forced changes in the character of internal variability. So for example, ENSO can change its frequency, its amplitude, spatial pattern, and teleconnections to remote areas as it responds to greenhouse gas increases and other aspects of anthropogenic emissions. Okay, so now I'll just introduce the tool that we'll be using, and then I'll get right on to the results. So our question really is, in general, how do the characteristics of internal variability change with climate change? So a very nice tool that I think is a really direct way to get at this question is to use the so-called snapshot EOF analysis approach. It's also called ensemble empirical orthogonal function analysis. So I'm sure many of you are familiar with traditional EOF analysis. So traditionally, EOF analysis is done in the time domain. So one gets a spatial pattern, and then you get the time series of that spatial pattern, which is corresponds to the each EOF. But importantly, if we did that to each ensemble member here, the spatial patterns are static. That's the way this traditional EOF analysis works. But if we're interested in how the spatial patterns may evolve with time, we can actually turn this on its head, if you will, and conduct EOF analysis across the ensemble dimension rather than across the time dimension. So this is given the name snapshot EOF analysis because it gives you a snapshot of the variability at each point in time. And importantly, the spatial patterns are free to evolve. This was introduced to climate science. I've listed a few papers here within the last 5 or 6 years. And I just think it's a really nice tool that we can avail ourselves of. So the reason why this works with a large ensemble is that, as I just showed you with the Nino 3.4 index example, each ensemble member at a given point in time gives us this random sampling of internal variability. So here is that same Nino 3.4 SST index in the year 1960, but rather than show you the time series, I'm showing you what that index looks like for each ensemble member, each of the 40 members on the y-axis here in the year 1960. And you can see that there are ensemble members that have very pronounced La Nina events, and then there are members that have pronounced El Nino events, and then there's a bunch of members that have neutral ENSO conditions. So it gives us a really nice sampling of the variability at a single point in time because we have so many ensemble members. So if you conduct an EOF analysis in this ensemble dimension, you're really looking, you have a lot of samples of internal variability to analyze. And so then you can repeat this snapshot EOF analysis for each time step in your model large ensemble, and then you thereby get the evolving patterns of these leading modes of variability. So just to ensure robust results here, we have decided to consider all samples within a 5-year window of the indicated year. So for example, for 1960 here, we have 40 ensemble members. We then pool all the years of these 40 members starting in 1950 all the way through 1962. So a 5-year window. So we have 200 samples for each of these snapshot EOFs. And this gives us added robustness. So I just want to emphasize, we're not doing a 5-year running mean. We're not low pass filtering the data. We're just pooling all of the samples from this 5-year window that is centered on the time step in question here. Okay, I hope that's clear. So as I said, this provides a really direct way to assess the evolving force changes in the leading patterns of internal variability. I think there's tons of applications for this methodology when you have a large ensemble to work with. Okay, so now we'll get on to the results. So as I said, we're going to be looking at the North Pacific Z500 snapshot EOFs 1 through 3. And I thought I'd just start by showing you how much variance each of these 3 modes explains as a function of time. So the first mode explains somewhere between 35 and 50% of the total variance over that North Pacific domain that I showed you earlier. So it increases a little bit, but not enormously. Mode 2 and 3, their fraction of variance explained stays pretty constant throughout the simulation period, around 20% for mode 2 and around 10% for mode 3. I won't explain what the shading is, but it's sort of an error bar to test whether these modes are well separated according to the North criterion. And as you can see visually, they are well separated at all time steps. And I can assure you that no mode mixing occurs. So mode 1, the PNA, always looks like the PNA all the way through the simulation, and so on for mode 2 and 3. Even though the fraction of variance explained by these modes doesn't change a lot, although it does increase a little bit for mode 1, the total variance of the Z500 field does increase over time, and it increases by about 25 to 30% from the beginning to the end of the simulations. Okay, now we'll look at the spatial pattern of this first mode, which I'm going to call the PNA. I realize that's not necessarily, a pure PNA, but we'll use that name for convenience. So this is, so what we do here, I'm showing you the map of the regressions of the Z500 field at each point over the globe onto the standardized PC from this snapshot EOF approach. So even though our domain for computing the EOF is enclosed in this red box in the North Pacific, we derive the global pattern that's associated with that mode by making this global regression map. And the stippling, or the dots on this map, are showing where these values are significant at the 99% confidence level, taking into account the false discovery rate. And just to reiterate, this is a pattern of variability. We are showing the positive phase just for convenience, but the negative phase is implicit. So in this case, you can see negative anomalies over the Aleutian Low region in the North Pacific, but that can just as easily be a positive anomaly. Okay, so that's what the pattern looks like in 1920. Now I'll give you an animation of what this snapshot EOF looks like as it evolves with time, as the radiative forcing, the greenhouse gas forcing, increases. So this will be an animation, and in this green box, you can pay attention to the year of the simulation. So it'll go all the way from 1923 all the way out to 2100. So here we go, and here's the animation. Now we're in the 1940s, and we're in the 1950s. And this pattern, you can see it still looks like a PNA pattern, not too different from what it looked like in 1920. And now we hit the mark about year 2010 and year 2020. And now you're beginning to see maybe some systematic change here compared to 1920. So now we're approaching the latter part of the 21st century, and here we are in the year 2098, or that last 5-year window. And you can see by the end of the simulation period, the amplitude of the variability has grown enormously. And so it's even off scale here in the Aleutian Low region. It's off of our color bar chart. It's intensified that much. And you can still recognize sort of the typical PNA structure, but I think you can also see that it has, sorry about that. I messed up with the animation. It has also expanded across the North Atlantic sector and has shown a stronger connection to the tropics. I apologize for short-circuiting the animation, but I'll show you what I mean with this illustration here. So now I want to get on to the precipitation impacts that are associated with this mode of circulation variability. So I'm not going to show you animations. I'll simply show you what this mode looks like in the year 1920 and the year 2100. And now what you're seeing are the contours. That's the Z500 field that was in the shading in the previous animation. So now the contours are the Z500 field, and the shading are the precipitation regression coefficients onto the standardized PC of this mode. So you can see how this mode affects or is associated with precipitation. So the green colors are positive precipitation anomalies, and the brown colors are negative anomalies. So as you can see, this mode evolves substantially over time, and the variability of this mode intensifies, it amplifies, and the associated precipitation also increases. And it has a large impact actually on precipitation over California. It produces a much stronger precipitation anomaly in the future compared to the past. You can also see that it has a stronger connection to the North Atlantic, both in terms of circulation and precipitation. And very evident is how the linkage to the tropical Indo-Pacific precipitation is strengthened by the end of the simulation. So now we can move on to mode 2. As I alluded to, we're giving this the name the North Pacific Oscillation / West Pacific pattern. Again, there are nuances with this nomenclature, but we'll use this for convenience. So mode 2 also shows a slight intensification, not as pronounced as mode 1 by the year 2100. It also shows an enhanced connection over the North Atlantic in 2100 compared to 1920. And you can see the connection to the tropical precipitation field is also enhanced in the future. In this case, a negative precipitation anomaly associated with this mode in the future. And then finally, mode 3, the so-called East Pacific pattern. Again, like the other two modes, it shows an intensification, and in this case, kind of an eastward shift. So it becomes particularly important for precipitation over Western North America, California in particular, but also along coastal British Columbia. And it shows an enhanced connection to the North Atlantic, and like the other modes, an enhanced connection to the tropics. So there's some common features to the future changes in these modes of variability. So that raises the question, how much of the force change in these extratropical modes of variability is due to the force changes in the tropical variability? So we've addressed that by looking at the tropical Pacific SST snapshot EOFs, and then ultimately removing their influence from the Z500 field, as I'll show you in a moment. So let me start by giving you evidence that there's a lot of influence from the tropical Pacific. So we've conducted the same snapshot EOF analysis on the tropical Pacific SST field. And so here, what I'm showing you is the first snapshot EOF in 1920. And I'm showing you the regressions of the Z500 field and the precipitation field onto this snapshot EOF of tropical Pacific SSTs. So the domain for the SST EOF is here in this red box. And then we're showing you the global regressions of the Z500 and precip onto that EOF. So this is sort of a typical canonical East Pacific ENSO pattern with sort of canonical atmospheric teleconnections to the Northern Hemisphere. This is what that EOF looks like in the year 2100. And you can see, like many models, there's an intensification of these East Pacific ENSO events with time, and the associated teleconnections to both the North Pacific and the North Atlantic are amplified over time. And mode 2, which is sort of a Central Pacific flavor, if you will, of ENSO variability, this mode also has connections to the North Pacific, and in the future, this mode is also projected to intensify and lead to enhanced teleconnection over the North Pacific, but really not much impact over the North Atlantic. So as I said, we can take these snapshot EOFs and we can regress out their influence from the global Z500 and precipitation field at each time step. And then we can recompute the North Pacific Z500 snapshot EOFs from that ENSO residual field. And that'll give us a way of teasing out the relative importance of changes in the tropics, in tropical variability versus changes in intrinsic mid-latitude variability. Okay, so here are the, you've seen this before. This is the snapshot EOFs for the total Z500 field in 1920 for modes 1, 2, and 3. So I showed you that a moment ago. And now this is what these modes look like when these two leading flavors of ENSO have been removed. And you can still recognize these modes, and that suggests that their spatial structure derives from intrinsic mid-latitude dynamics. And then the way to interpret this, the total field, is the intrinsic mid-latitude dynamics plus the projection of ENSO teleconnections onto these modes in 1920. And so you can definitely see some difference, but it's not that big in 1920. And now let me show you the same thing, but this is now for the year 2100, so at the end of the simulation. And now if you compare the total field with the no ENSO depiction of these modes, you can see that we've been successful in removing much of the tropical influence. You don't see much to speak of in terms of tropical precipitation anomalies here. And the modes are recognizable still without the influence from the tropics, but you can see that the tropics do play a role in producing the snapshot EOFs from the total field. That is, for example, if we look at mode number 3 here at the bottom, you can see in the North Atlantic sector, it's evident that the influence from the tropics is really driving this North Atlantic teleconnection because it's absent in the depiction of this mode that excludes the influence from the tropics. Okay, so and now I'm just showing you side by side what these modes look like when these ENSO EOFs, their influence is removed. So this is now a side-by-side comparison of the modes from in 1920 and 2100 that is attributable to intrinsic mid-latitude dynamics. And now if we look at these modes, for example, mode 1, 1920 and 2100, you can see it has intensified somewhat, and the connection to the North Atlantic has been enhanced, but less so than what we saw for the total field. Mode 2 doesn't change a whole lot from 1920 to 2100. Mode 3 shows kind of an eastward shift in 2100 compared to 1920, and also some amplification over the western part of the North Atlantic. So the final result that I want to show you is this comparison of or decomposition of these EOFs into their intrinsic component, so the no ENSO component, and the component due to the ENSO influence. And I'll summarize these results by showing you the linear trends in these snapshot EOFs. So remember, we have EOFs for each time step, so we can simply fit a linear trend at each grid point of these EOFs, and then we can thereby derive the spatial pattern of the trends in these modes from 1920 to 2100. Okay, so here's what that looks like. So these are linear trends in mode 1. This is the PNA, if you will. So it's not the PNA itself, it's the trend in the PNA as it evolves over time due to the radiative forcing. So on the left, you're seeing the total field or the total snapshot EOF, and the PNA, you can see there's a low pressure over the North Pacific, indicative of a deepening or an enhancement of the variability. And then you can see sort of an NAO type structure in the North Atlantic in the contours in the Z500 field. And associated with that is a signature in tropical Pacific precipitation. Then if we decompose it into the intrinsic mid-latitude component by removing these influence of these two ENSO EOFs, you can see that some of the intensification of the mode in the North Pacific and in the NAO, the North Atlantic region, a lot of that or some of that stems from just mid-latitude dynamics. And then if we subtract this intrinsic component from the total, one sees the tropical influence. And that has a different pattern. As ENSO evolves with time, so do its teleconnections. And that projection of those teleconnections onto this PNA pattern is what's shown here. So both pathways contribute. Excuse me. This is what the linear trends look like for mode 2, and I won't belabor the point, but again, both pathways contribute. Both the intrinsic mid-latitude dynamics change with time, and that helps to amplify this pattern, and also the teleconnections from primarily actually from the second ENSO mode also affects this pattern. And then finally, mode 3, this East-Pacific pattern, I find it very interesting that the trends in this pattern have a very distinct structure that is attributable to the intrinsic dynamics versus the projection of the future changes in the ENSO teleconnections onto this mode. What the underlying dynamics of these two contributions is, that still remains to be understood, but it's very clear that there are very, very important and strong signals from both of these influences. Okay, so I'm going to end with just a single slide here on whether we need to pay attention to these force changes in the variability. So the question here is, how large are the force changes in these internal modes of variability compared to the force changes in the mean state? So here on the top here is a typical IPCC style figure, if you will, where we're looking at the mean state change, the year 2100 minus 1920 from the CESM1 Large Ensemble. So again, the color scheme is the same. Precip is in the shading, and then the Z500 field is in the contours. So that's how the mean background climate is changing due to anthropogenic forcing. Then in the red box here, these are how these three leading modes of Z500 from the snapshot EOF approach and their associated precipitation fields, what those modes look like in the year 2100. And this is per standard deviation of the modes. So really, you can multiply these panels by 2 to get kind of their 5th to 95th percentile range. And you can immediately see just from the number of contours and the degree of shading here that even in the year 2100, these internal modes of variability are so large that they can overwhelm this forced response. And it may actually be very hard to attribute anything that we see in the year 2100 in these fields to the mean state change, but rather to internal variability and their force changes thereof. So I think that's just an important message. And then here's just one other way of looking at it, which is to look at the time the linear trends through time. So the top is the ensemble mean or the forced response, the trends in the mean state. And then in the red box, these are the trends that I just showed you a moment ago in these internal modes of variability. And here, the picture is a little bit different in terms of the relative amplitudes of the chain of the trends in the mean state versus the trends in the internal modes. But if you look at mode number 3, the Z-specific pattern, and if you look especially at the Z500 field, you can see that the magnitude of the trends in this field, in this mode, are about the same order as the trends in the mean state in the Z500 field. So I think forced changes in the internal variability may be, something to pay attention to as we look in the future. Okay, so I'm going to wrap up with a few summary conclusions. So again, I think these large ensembles are a really nice test bed or window into looking at force changes, not only in the mean state, but also in the internal variability. And I think a nice tool to use is this snapshot EOF analysis. It's a very direct way of trying to look at these force changes. So for our study, and as I say, this is just carving out, the tip of the iceberg. We looked at the North Pacific Z500 variability in boreal winter, and we find that the leading modes intensify in the future. They expand their spatial footprint into the North Atlantic and show enhanced linkages to ENSO in the future. And somewhat surprisingly, the third mode, the East-Pacific pattern, shows the largest force change through time. Secondly, it's clear that both tropical teleconnections and intrinsic mid-latitude atmospheric dynamics both play a role in these forced changes. And then finally, future changes in variability can be roughly the same order of magnitude as those in the mean state and can overwhelm the mean forced response even by the end of this century. So open questions, lots of open questions. How model dependent are these results? And very importantly, what are the underlying dynamics that underpin these changes? And are there any emergent constraints that can be brought to bear on these model results that can help with assessing the realism of their future projections? Our next steps, I hope, will be to apply a similar analysis to other model large ensembles, other regions, other seasons. And I point you to this nice multi-model large ensemble archive that was put together by a US CLIVAR working group on large ensembles, co-chaired by Keith Rogers and myself. And it's just a very convenient repository of large ensembles. And then we'd like to implement this snapshot EOF methodology in a diagnostics package that we've developed here in the Climate Analysis Center at NCAR, the so-called Climate Variability Diagnostics Package for Large Ensembles. And this is really how this research got started, was through that package. So if you're not familiar with it, you can find it on the NCAR website. So with that, I appreciate your attention and I look forward to your comments and feedback. Thanks so much.
Thank you, Dr. Desser. And if anyone has any questions, this is the time you can raise your hand, or you can just unmute yourself, or if you don't have a microphone, you can type it in the chats. Sumons, go ahead. You should be able to unmute yourself.
Hi, Clara. Thanks for a very nice talk. You explained the snapshot EOFs well. But when one tries to get a principal component, because the patterns have slightly different structure at different points in time, how confident are we that the principal component is a true principal component that can be used to monitor changes?
Thank you, Sumant. I skipped over that
Okay.
point, but I will just say it now. So I appreciate your question. The principal components are actually a function of ensemble member, not time. So so for a given time, we have the snapshot EOF spatial pattern, and then we have the amplitude of that pattern in each ensemble member. So those are the PC values, principal component values. And then we have a separate principal component at each time step, because as you say, the EOF changes its pattern. So you can't use a snapshot EOF, a snapshot principal component to monitor the mode through time. But I think what you can do is to regress the data onto the evolving snapshot EOFs, I guess, to get the representation of that mode in, if you were to do it with observations, say, the amplitude of that mode at any given time. Does that make sense?
Yeah, because you were using mode 1 at the beginning of the century, and mode 1, continue to label it mode 1, despite some changes in its structure.
Right.
Yeah.
It's exactly, it is still recognizable, I would say, as the
mode
PNA in the EOF domain. But the important thing is we've allowed its structure to amplify, to evolve. But I would say we can still call it mode. It is still mode 1.
Yes.
What we call it maybe is another question, but it remains the leading mode. I showed you that in the fraction of variance explained. But very helpful questions. Thank you.
Okay, thank you.
Yeah. By the way, I think I know that you've really shown the value of rotated EOFs. I think a really nice further step that I think has not, to my knowledge, been done is to use a rotated snapshot EOF approach, which I think would be straightforward. And I'd love to correspond with you on that if that's something you think would be of value.
Okay, thank you.
Yep.
Thank you. So Claudia Tabaldi put a question in the chat a while ago. So I see your hand, Weston, but I want to give Claudia a chance to talk.
Hi, Clara. Nice to see you. Thank you for the usual nice talk. You must have said this, but still trying to digest these snapshot EOFs. Are you running those over anomalies with respect to the ensemble mean?
Exactly. So
okay.
Right. So thank you. I could have said that better. So let's say a given year, 1960, we have our 40 ensemble members, or in our case, we have 200 samples, but 40, you can think of that. And so then when you do EOFs, you remove the mean of the sample before you do EOF analysis.
Yeah.
In our case, the mean of the sample is simply the ensemble mean in 1960, and the ensemble mean then is, an estimate of the forced response by virtue of the large ensemble design. So they are anomalies with respect to the ensemble mean at each time step.
Yeah, and the other thing I will say, but not take more time, is that I'd be really curious to know if you think you need all 40 ensemble members, or if you could get away with 20 or 25, because I just wrote a paper that says we don't need more than 25. Well, but I'll talk to your co-author.
Let's correspond about that.
Yes.
I
don't want to say.
We actually found that, as I said, we did this 5-year window to actually augment our sample size.
Yeah.
And I think it depends on, how carefully one wants to represent these patterns. And we found that especially the higher order modes could be subject to some uncertainty or a little bit of mode mixing between modes 2 and 3, which had more comparable percent variance explained. And we found that when we, did this enhanced sampling, that we didn't have to worry about that.
That's exactly what I did in my paper, 5-year window. But thank you. Bye.
No, bye-bye. Thank you. We'll keep in touch.
Weston, you can go ahead.
Yeah, thanks, Clara. Super interesting talk. I was wondering what you saw as the greatest potential for some of these snapshot EOFs. I think it's an interesting approach, the extent that I've sort of wrapped my head around it. I mean, what you've outlined was all looking at linear trends and the changes in these modes. Could you use this to look at something like the nonlinear forced response of some of these modes of variability, or separating out something like an equilibrium from a transient response? I know there's sort of maybe a lot of other applications to this.
Those are excellent ideas. Absolutely. Absolutely. I think one could look at, the shape of the changes in time, i.e. whether, there are, I'm sure things are not linear. That was just a convenience. I've been thinking about looking actually at the time of emergence of the force changes in the internal variability. And I think that's maybe similar to what you're thinking about of equilibrium versus transient. I think that could be, it's just something I haven't gotten to. I think, I really like your idea. And I know from having looked at the changes in ENSO in various models, not work that I've done by on my own, but with others, that the changes in ENSO amplitude and pattern are very far from linear. And in fact, they saturate in some models kind of mid-century, and then can even decline by the end of the century. So that tropical influence on these extratropical modes, I think there's a lot more to be learned about the temporal nature of that tropical influence. And I think the way we've shown it in terms of linear trends, that doesn't do justice to actually probably everything that's going on. And then the last remark I'll make is, we've done, of course, a linear analysis by virtue of EOFs. But we have, of course, there are definitely questions, especially with regard to tropical influence, whether you can really treat, warm and cold phases of ENSO events as having the same extratropical teleconnections. So we actually, in our paper, we have a very hefty supplemental materials that shows what these snapshot EOF modes look like in early and late in the simulation for the positive and negative phases of these principal components. So there are some non-asymmetries with respect to phase, but they're not first order. But I think there's still more to be done on that. I'd be very happy to follow up on some of your thoughts on an email. I'd love to get to know your work and what you're interested in. So thanks a lot.
Suma, did you have something to add to that?
Yes. Clara, when reanalysis is done, now there are several ensemble members in reanalyses, I believe, perhaps at the European Center and certainly for the 20th century reanalyses. Has anybody done something like this using ensemble members in the reanalysis to track in the observed record how things have changed?
So first of all, not that I know of, but then I'm wondering about, I don't know much about, I mean, yes, I'm familiar with the ensemble reanalysis or ensemble reanalysis ensembles, but is it the same kind of ensemble that we are doing with our models, or is it more observational uncertainty in terms of measurement error and sparseness of data rather than true? I don't think these ensembles of reanalyses would have El Nino events in different years, right?
That's true.
82, 83 El Nino would still be 82, 83 in all of them. So I think it's a different, I think one could use snapshot EOFs to look at the influence of observational uncertainty on modes of variability, but it's not the same uncertainty as we're, isolating in these large ensembles.
But it might still be a way to document the change in the internal variability modes, even though ENSO is not is time locked in some sense, but the greenhouse gas concentrations have gone up and in the 20th parts of the 21st century. So there might be something there. I don't know. I was just asking.
Yeah.
And I had one other observation in the early slides where you were showing us ensemble member 1, 2, and 3, and you took out the mean state and you showed us the Nino 3.4 index. There was visually the sense that the variability was decreasing towards the latter decades. On the other hand, the ENSO EOFs that you showed towards the latter part of your talk, ENSO seemed to be much stronger towards the end of the record. Yes, it's that one.
I know, exactly. I'm not going to share the screen, but hopefully you can see it.
Yes.
So I think this comes back to Weston's point about nonlinearities. And yeah, you can definitely see, and I know this for a fact, that in the CESM1 Large Ensemble, ENSO, or at least Nino 3.4 variance, actually is strongest around the 2040s, which you can see visually.
Yes.
Then it's a little bit less by the end of the century, but end of century variance is still larger than the beginning.
At the beginning. Yeah.
It's a little hard to see from just 3 members, but you can take my word for it. But this is a case in point, I would say, to Weston's idea that, in fact, we may even see in this model large ensemble, if we looked at this intermediate time of the 2040s, that the tropical influence might be even larger than what it is at the end of the century. And these could be very important things to look at across different model large ensembles, which definitely have diversity in terms of, even though ENSO tends to amplify in each of those model large ensembles, it does so at different times. And I do wonder if that's part of, would be interesting if this idea of emergent constraints, if the uncertainty across different model large ensembles is stemming primarily from their different behavior of future changes in ENSO, and maybe the intrinsic mid-latitude dynamics is more, consistent across models. It's just something I'm interested in pursuing. I haven't done it yet.
And if I may squeeze one more last question, you chose the 500 millibar level for analysis.
Yeah.
And we know historically from teleconnection analyses, Wallets and Gutzler, and the numerous others that followed, that one could never get the ENSO teleconnection as being part of the teleconnections one identified at the 500 millibar level, because the tropical response is more baroclinic, and it might be better if you wanted to begin to resolve the tropical teleconnection from a teleconnection analysis or something, you might be better off being in the upper troposphere or lower troposphere, perhaps the upper troposphere, because things would propagate there.
Yeah, thank you. I think that's a really good point. I think we're not, my sense is that in the extratropics, so poleward of 30 degrees north, I think what we see in the 500 millibar height field and 200 would probably be quite similar. I think it's equivalent barotropic once you get poleward 30 degrees, but certainly in the subtropics and tropics, probably that's 500 is the worst place to look because of the baroclinic structure. I think that that's a really good point, and I think maybe something like a upper level, maybe 300 hectopascal stream function
Would be the great.
very nice lens to look at things. That's a very nice point. Yeah.
Thank you. Thank you. Very nice. Thank you.
Thank you. I want to cue Michelle Leroux, who has been waiting for a while.
Great. I love the questions. Happy to stay as long as you want.
Hi, Clara. Thanks so much. That was a really great seminar. Lots of food for thought. You kind of quickly referenced you're still trying to understand the dynamics around this, but I still want to make you uncomfortable and ask whether you've thought a little bit more about why we would see this increase in variance and intensity. I realize that the answer for the tropics may be very different from the extratropics. In fact, I think the extratropics part puzzles me more because of what you mentioned, which is like the work that you've done with James Screen, showing the, the variance, at least the temperature equator to pole gradient tends to reduce. So I'm having trouble reconciling that with what we know about radiative forcing in the mean and why variance would increase. Any thoughts?
Well, thanks, Michelle. I like that question. Makes me, that's the harder work, is to really think about things. I think, speaking to your point about the, mid latitudes and the pole to temperature gradient, I think we should think differently about the lower tropospheric pole to temperature, equator to pole temperature gradient versus the upper troposphere. I mean, certainly Arctic sea ice loss reduces the gradient at low levels, but I think because, the tropics warm and move upward, that actually that meridional temperature gradient across mid-latitudes in the upper troposphere increases.
That's right.
And I think that these modes of variability, at least looking at the Z500 field and probably above, that we're probably, it's a great question, but maybe we're not, the influence from the sea ice loss is not manifesting as strongly when we look at the mid and upper troposphere. Why?
So it would be interesting maybe to do this with low level field versus a high level.
Yeah,
see if that's right. I think that would be really interesting.
Yeah, I think as the temperature gradient, the mean north-south temperature gradient in the mid to upper troposphere, if that is pushed northward and in the mean and maybe tightens a bit, then you might expect that, you have more energy for, this variability in the dynamics. But it's a really good point to look at the lower levels. And the other thing I've been thinking about how to extend this work is to also look at the synoptic variability that is associated with each one of these modes, and just to see how it plays out in terms of the actual, storm systems that are organized by these large scale modes. And again, there might be some differences between lower levels and upper levels that remains to be seen.
No, those are great ideas. Thanks, Clara.
Thank you, Michelle.
Thank you. Well, that's all of the questions that I have. So unless anyone has any last minute questions, and if you just go ahead and raise your hand now. Okay, that was my cue. Then we can close off today's seminar. So thank you everyone for coming, and thank you to Clara for giving us this great talk. This was wonderful. I hope you all join us next week as we continue our seminar series. And if anyone wants to review any of, oh, here I can take it from you, Clara. I see what you're doing. If anyone wants to review this seminar, will be up as a video probably by the end of the week.
Thanks so much, everybody. Such a pleasure to talk with you. Bye-bye.
Have a good day, everybody.
Bye-bye.